The National Electrical Code, or NEC, does not mandate a lightning protection ground rod bonded to each light pole. However, the NEC strongly recommends grounding light poles to a grounding electrode system as outlined in Article 250. Article 250.50, specifically addressing lighting equipment, states that metallic lighting equipment, luminaires, and lamp holders shall be grounded. The grounding of lighting equipment must be achieved through one of two methods: firstly, by connecting to the metal raceway of the supply circuit, or secondly, by a separate grounding conductor run with the circuit conductors and connected to the equipment and to the grounding electrode system. Although the NEC doesn't explicitly require lightning protection ground rods on individual light poles, it does stipulate that all metallic lighting equipment must be grounded. Therefore, if a light pole is metallic, it must be grounded by either connecting it to the metal raceway of the supply circuit or by running a separate grounding conductor to the grounding electrode system. The purpose of grounding electrical systems and equipment is to provide a low impedance path for fault current to return to the source, which helps to quickly trip a circuit breaker or fuse and clear the fault. This protects people from electric shock and prevents damage to equipment. Grounding also helps to stabilize voltage during normal operation, which can reduce electrical noise and improve the performance of sensitive electronic equipment. The grounding electrode system is a network of interconnected grounding electrodes that provide a common reference point for grounding electrical systems and equipment. The grounding electrode system typically includes one or more of the following: firstly, a metal underground water pipe that is in direct contact with the earth for at least 10 feet. Secondly, a ground ring encircling the building or structure, buried at least 2.5 feet below the surface. Thirdly, a concrete encased electrode consisting of at least 20 feet of bare copper conductor at least 493 inches in diameter encased in at least 2 inches of concrete, located within the bottom of a concrete foundation or footing that is in direct contact with the earth. Fourthly, a ground rod or pipe electrode that is at least 8 feet long and driven into the earth. And fifthly, other listed grounding electrodes. The grounding electrode system must be bonded together to form a single grounding electrode system. This bonding is typically accomplished using a grounding electrode conductor, which is a copper conductor that connects the grounding electrodes together. The size of the grounding electrode conductor is determined by the size of the service entrance conductors. The grounding electrode conductor must be connected to the neutral conductor at the service entrance. This connection is known as the main bonding jumper. The main bonding jumper provides a path for fault current to return to the source. In addition to the NEC requirements, local building codes or utility regulations may impose additional lightning protection measures. It's always advisable to consult with local authorities to ensure compliance with all applicable codes and regulations. This might involve installing lightning rods, surge protection devices, or implementing specific grounding techniques tailored to the local environment and risk factors. Lightning protection systems are designed to protect structures and their occupants from the harmful effects of lightning strikes. A typical lightning protection system consists of, firstly, air terminals, also known as lightning rods, which are installed in the roof of a building or structure to intercept lightning strikes. Secondly, down conductors, which are heavy-gauge copper or aluminum conductors that provide a low-impedance path for lightning current to flow from the air terminals to the grounding electrode system. Thirdly, grounding electrodes, which are used to dissipate the lightning current into the earth. The grounding electrode system for a lightning protection system is typically more extensive than the grounding electrode system for an electrical system. This is because lightning currents are much larger than fault currents. Surge protection devices, or SPDs, are designed to protect electrical equipment from voltage surges, including those caused by lightning strikes. SPD are typically installed at the service entrance and at branch circuits. SPD work by diverting surge current to ground, thereby protecting the connected equipment from damage. Grounding techniques are a critical aspect of lightning protection. Proper grounding ensures that lightning current is safely dissipated into the earth, minimizing the risk of damage to structures and equipment. Different grounding techniques may be employed depending on the soil conditions, the size of the structure, and the level of lightning activity in the area. Some common grounding techniques include firstly, using multiple ground rods connected in a grid pattern, secondly, using a ground ring encircling the structure, thirdly, using a concrete encased electrode. When designing a grounding system, several factors must be considered. Firstly, soil resistivity, secondly, the size and type of structure, thirdly, the level of lightning activity in the area, fourthly, local codes and regulations. Soil resistivity is a measure of how well the soil conducts electricity. Soil with high resistivity is more difficult to ground than soil with low resistivity. The size and type of structure will also affect the design of the grounding system. Larger structures require more extensive grounding systems than smaller structures. The level of lightning activity in the area is another important factor to consider. Areas with high lightning activity require more robust grounding systems than areas with low lightning activity. Local codes and regulations may also specify certain requirements for grounding systems. Therefore, consulting with a qualified electrical engineer or a lightning protection specialist is essential to ensure that the grounding system is properly designed and installed. Also, proper maintenance of grounding systems is crucial to ensure continued effectiveness. Grounding connections should be inspected regularly for corrosion or damage, and any necessary repairs should be made promptly. Soil conditions can change over time, affecting the effectiveness of the grounding system. Periodic testing of the grounding system is recommended to verify its performance and identify any potential problems. When installing or maintaining grounding systems, always follow safe work practices. Wear appropriate personal protective equipment, such as gloves and eye protection. De-energize electrical circuits before working on grounding connections. Use insulated tools to prevent electrical shock. Be aware of underground utilities and avoid digging in areas where they may be present. In summary, while the NEC does not mandate lightning protection ground rods on each light pole, it emphasizes the importance of grounding all metallic lighting equipment. Furthermore, local codes and regulations may require additional lightning protection measures. Consulting with qualified professionals and adhering to safe work practices are crucial for ensuring effective grounding and lightning protection. The grounding electrode system should have a resistance to ground of 25 ohms or less. If the resistance to ground is greater than 25 ohms, an additional grounding electrode must be installed. The grounding electrode conductor must be protected from physical damage. If the grounding electrode conductor is exposed to physical damage, it must be installed in conduit or other suitable protection. The grounding electrode conductor must be continuous. The grounding electrode conductor must not be spliced. The grounding electrode conductor must be securely fastened to the grounding electrode. The grounding electrode conductor must be securely fastened to the equipment grounding conductor. The equipment grounding conductor must be sized in accordance with NEC Table 250.122. The equipment grounding conductor must be installed in the same raceway or cable as the circuit conductors. The equipment grounding conductor must be connected to the equipment grounding terminal of the equipment. The equipment grounding terminal must be identified with a green marking. The equipment grounding terminal must be accessible. The equipment grounding terminal must be securely fastened to the equipment. The equipment grounding terminal must be made of a corrosion-resistant material. The equipment grounding terminal must be sized in accordance with NEC Table 250.122. The equipment grounding conductor must be continuous. The equipment grounding conductor must not be spliced. The equipment grounding conductor must be securely fastened to the equipment grounding terminal. The equipment grounding conductor must be securely fastened to the grounding electrode conductor. In addition to the general grounding requirements, there are also specific grounding requirements for certain types of equipment. For example, motors must be grounded in accordance with NEC Section 430.12. Transformers must be grounded in accordance with NEC Section 450.10. Generators must be grounded in accordance with NEC Section 445.14. In addition to the NEC requirements, there may also be local codes or regulations that apply to grounding. It is important to check with the local authorities to ensure that all applicable codes and regulations are being followed. Proper grounding is essential for electrical safety. Proper grounding helps to protect people from electric shock and to prevent damage to equipment. By following the NEC requirements and any applicable local codes or regulations, you can help to ensure that your electrical system is properly grounded. When referring to Article 250, it is important to note that this article covers a wide range of grounding and bonding requirements. It is essential to carefully review the specific sections of Article 250 that apply to your particular situation. For example, Section 250.4 provides general requirements for grounding and bonding. Section 250.24 provides requirements for grounding separately derived systems. Section 250.30 provides requirements for grounding electrode systems. Section 250.50, as discussed earlier, provides requirements for grounding lighting equipment. Section 250.118 provides requirements for equipment grounding conductors. Section 250.122 provides requirements for sizing equipment grounding conductors. Section 250.130 provides requirements for methods of equipment grounding. Section 250.146 provides requirements for connecting receptacle grounding terminals to the equipment grounding conductor. Understanding these different sections of Article 250 is crucial for ensuring that your electrical system is properly grounded and bonded. Furthermore, it is important to stay up to date with the latest edition of the NEC. The NEC is updated every 3 years, and changes are often made to the grounding and bonding requirements. By staying up to date with the latest edition of the NEC, you can ensure that your electrical system is in compliance with the most current standards. Remember, grounding is not just about meeting code requirements. It is about protecting people and property from electrical hazards. Proper grounding can help to prevent electric shock, fire, and equipment damage. Therefore, it is essential to take grounding seriously and to ensure that your electrical system is properly grounded and bonded. The size of the grounding electrode conductor is determined by NEC Table 250.66. For example, if the service entrance conductors are 4/0 American wire gauge copper, the grounding electrode conductor must be at least #2 American wire gauge copper. The grounding electrode conductor must be connected to the neutral conductor at the service equipment. This connection is called the main bonding jumper. The main bonding jumper must be sized in accordance with NEC Table 250.28. For example, if the service entrance conductors are 4/0 American wire gauge copper, the main bonding jumper must be at least #2 American wire gauge copper. The equipment grounding conductor must be sized in accordance with NEC Table 250.122. For example, if the overcurrent protection device is rated at 20 amps, the equipment grounding conductor must be at least #12 American wire gauge copper. The equipment grounding conductor must be installed in the same raceway or cable as the circuit conductors. This helps to ensure that the impedance of the grounding path is low. The equipment grounding conductor must be connected to the equipment grounding terminal of the equipment. The equipment grounding terminal must be identified with a green marking. The equipment grounding terminal must be accessible for inspection and testing. The equipment grounding terminal must be securely fastened to the equipment. The equipment grounding terminal must be made of a corrosion-resistant material. Proper installation and maintenance of grounding systems are crucial for electrical safety. Neglecting these aspects can lead to serious consequences, including electrical shock, fire hazards, and equipment damage. Always consult with qualified professionals and adhere to relevant codes and regulations to ensure the safety and reliability of your electrical systems. Consider the specific application of the light poles. For instance, light poles located in areas with high lightning activity, such as coastal regions or open fields, may benefit from enhanced lightning protection measures beyond the basic NEC requirements. Light poles used for critical infrastructure, such as emergency lighting or airport runway lighting, may also warrant additional protection to ensure continuous operation during adverse weather conditions. Evaluate the soil conditions at the installation site. Soil resistivity plays a significant role in the effectiveness of grounding systems. High soil resistivity can impede the flow of fault current to ground, reducing the effectiveness of the grounding system. In such cases, soil improvement techniques, such as the addition of ground-enhancing materials, may be necessary to lower the soil resistivity and improve the performance of the grounding system. Assess the potential for corrosion of grounding components. Grounding electrodes, conductors, and connections are susceptible to corrosion, especially in harsh environments such as coastal areas or industrial sites. Corrosion can degrade the performance of the grounding system and increase the risk of electrical hazards. To mitigate corrosion, use corrosion-resistant materials such as copper-clad steel or stainless steel, and apply protective coatings to grounding components. Regularly inspect and test grounding systems to identify and address any signs of corrosion. Consider the use of surge protection devices, or SPDs, to protect electrical equipment from voltage surges. SPD are designed to limit the magnitude of voltage surges and divert surge current to ground, protecting sensitive electronic equipment from damage. SPD can be installed at the service entrance, at branch circuits, or at individual equipment locations. Choose SPD with appropriate voltage and current ratings for the application. Ensure that SPD are properly grounded to provide an effective surge protection path. Implement a comprehensive grounding and bonding plan. A well-designed grounding and bonding plan is essential for ensuring electrical safety and equipment protection. The plan should address all aspects of grounding and bonding, including the grounding electrode system, equipment grounding conductors, bonding jumpers, and surge protection devices. The plan should be documented and readily available for reference. Train personnel on proper grounding and bonding practices. Electrical workers should be trained on the importance of grounding and bonding and on the proper procedures for installing, inspecting, and maintaining grounding systems. Training should cover relevant codes and standards, safe work practices, and the use of appropriate tools and equipment. By investing in training, organizations can help to ensure that their electrical systems are properly grounded and bonded, reducing the risk of electrical hazards. Periodically review and update the grounding and bonding plan. Electrical systems and equipment can change over time, so it is important to periodically review and update the grounding and bonding plan to ensure that it remains effective. The review should consider any changes to the electrical system, such as the addition of new equipment or the modification of existing circuits. The review should also consider any changes to relevant codes and standards. By periodically reviewing and updating the grounding and bonding plan, organizations can help to ensure that their electrical systems are always properly grounded and bonded. Remember that grounding and bonding are not one-time tasks. They are ongoing processes that require attention to detail, adherence to codes and standards, and a commitment to electrical safety. By following these best practices, organizations can create safe and reliable electrical systems that protect people and property from electrical hazards. The NEC provides specific requirements for the type and size of grounding electrodes that must be used. These requirements are based on factors such as soil conditions, the size of the electrical system, and the type of equipment being grounded. Common types of grounding electrodes include ground rods, ground plates, and underground metal water pipes. The NEC also specifies the minimum size and length of grounding electrodes. For example, a ground rod must be at least 8 feet long and must be made of copper or galvanized steel. The NEC also provides requirements for the installation of grounding electrodes. Grounding electrodes must be installed in a location where they will be in continuous contact with the earth. They must also be protected from physical damage. The NEC requires that all metallic equipment enclosures be grounded. This includes equipment enclosures such as electrical panels, junction boxes, and motor housings. Grounding equipment enclosures helps to prevent electrical shock hazards. The NEC provides specific requirements for the type and size of equipment grounding conductors that must be used. These requirements are based on the size of the circuit conductors that supply the equipment. The NEC also requires that equipment grounding conductors be installed in the same raceway or cable as the circuit conductors. This helps to ensure that the impedance of the grounding path is low. The NEC requires that all electrical systems be bonded together. Bonding is the process of connecting all metallic parts of an electrical system together to create a low impedance path for fault current. Bonding helps to prevent electrical shock hazards and to reduce electrical noise. The NEC provides specific requirements for the type and size of bonding conductors that must be used. These requirements are based on the size of the circuit conductors that supply the equipment. The NEC also requires that bonding conductors be installed in a way that ensures that they will remain in continuous contact with the metallic parts of the electrical system. The NEC requires that all grounding and bonding connections be made using approved methods. Approved methods include using listed connectors and fittings. The NEC also requires that grounding and bonding connections be made in a way that ensures that they will remain tight and secure. The NEC requires that all grounding and bonding systems be inspected and tested periodically. This helps to ensure that the grounding and bonding systems are functioning properly and that they are providing adequate protection from electrical hazards. The NEC provides specific requirements for the type of tests that must be performed. The NEC also requires that the results of the tests be documented. In addition to the NEC requirements, there may also be local codes or regulations that apply to grounding and bonding. It is important to check with the local authorities to ensure that all applicable codes and regulations are being followed. Proper grounding and bonding are essential for electrical safety. By following the NEC requirements and any applicable local codes or regulations, you can help to ensure that your electrical system is properly grounded and bonded and that you are providing adequate protection from electrical hazards. It's also crucial to consider the type of soil when implementing the grounding. Rocky or sandy soil would require different approaches compared to clay soil due to varying levels of conductivity. In regions with poor soil conductivity, consider using multiple ground rods spaced apart or ground-enhancing compounds to improve the effectiveness of the grounding system. Remember to consult with a qualified electrician to determine the best grounding solution for your specific site conditions. Ensure that all grounding connections are accessible for inspection and maintenance. This is important for identifying and addressing any potential issues, such as corrosion or loose connections, which can compromise the effectiveness of the grounding system. Regularly inspect grounding connections and tighten any loose connections to maintain a reliable grounding path. Also, protect grounding connections from physical damage and environmental factors, such as moisture and chemicals, which can accelerate corrosion. Proper signage should be placed to clearly identify the location of grounding electrodes and conductors. This helps prevent accidental damage during excavation or other activities. The signage should also indicate the purpose of the grounding system and any relevant safety precautions. In addition to visual inspections, electrical testing should be performed periodically to verify the integrity and effectiveness of the grounding system. This includes measuring the resistance to ground and performing continuity tests to ensure that all grounding connections are intact. The results of the electrical testing should be documented and compared to previous test results to identify any trends or anomalies. Regular maintenance of the grounding system is essential for ensuring its long-term reliability and effectiveness. This includes cleaning and lubricating grounding connections, replacing corroded or damaged components, and retesting the grounding system after any modifications or repairs. A well-maintained grounding system provides a reliable path for fault current to ground, protecting people and equipment from electrical hazards. Surge protection devices, or SPDs, are an important component of a comprehensive electrical protection system. SPD are designed to protect electrical equipment from voltage surges, such as those caused by lightning strikes or switching transients. SPD work by diverting surge current to ground, thereby limiting the voltage across the protected equipment. SPD should be installed at the service entrance and at branch circuits to provide comprehensive surge protection. The SPD should be selected based on the voltage and current ratings of the electrical system. The SPD should be properly grounded to provide an effective surge protection path. The NEC provides specific requirements for the installation and grounding of SPD. Proper coordination between the grounding system and the SPD is essential for effective surge protection. This includes ensuring that the grounding impedance is low and that the grounding conductors are properly sized. Regular inspection and testing of SPD is essential for ensuring that they are functioning properly. SPD should be replaced if they have been subjected to a significant surge event or if they are showing signs of wear or damage. It is important to consider the overall electrical system design when implementing grounding and bonding practices. This includes factors such as the type of equipment being used, the voltage and current levels, and the potential for fault currents. The grounding and bonding system should be designed to provide adequate protection for all electrical equipment and personnel. Proper coordination between the grounding and bonding system and other electrical protection devices, such as circuit breakers and fuses, is essential for ensuring the safety and reliability of the electrical system. A comprehensive approach to electrical system design, grounding, and bonding can help to minimize the risk of electrical hazards and to ensure the safe and reliable operation of electrical equipment. If you are unsure about any aspect of grounding and bonding, it is always best to consult with a qualified electrician or electrical engineer. These professionals have the knowledge and experience to design and install grounding and bonding systems that meet the requirements of the NEC and other applicable codes and standards. Investing in professional assistance can help to ensure the safety and reliability of your electrical system.